This is the Introduction to VLSI Design class, and this time we will talk about the sequential circuit design. So, we will talk first about sequencing and the sequencing element design, the max and min delay, clock skew, the time borrowing, and also two-phase clocking. So basically, we will introduce new clocking methodology that you might not have seen before. Sequencing, we have combinational logic and sequential logic. Any digital design, either it's going to be combinational or sequential. In the combinational logic, the output depends on the current inputs. In the sequential logic, the output depends on the current and the previous inputs, which requires separating previous, the current, and the future states. It's called sometimes states, sometimes it's called tokens. In our course, we usually call them states. Some examples that you might have heard about, the finite state machine or the FSM, also the pipelining. So in the finite state machine, you have a certain flip-flops or a certain storage elements, and you want the next state function, and you get it by having the combination logic equation, and then you build the block based on that. You have the inputs entering the combination logic, and based on that you have the next state function, and you get the output, and you can get feedback into the combinational logic as well. This is using the finite state machine. In the pipelining, you have registers that saves the current state, followed by a certain combination logic that do a certain job, and then again saving the status, another combination logic, saving the status, and so on. So, for example, in the MIPS, you have fetch, decode, execute, and accessing the memory, and then the last stage is write back, where we have 5 stages. In this example, we have only 2 stages with 3 status registers. So we have different sequencing examples. The sequencing actually, if the tokens moves through pipeline at a constant speed, there is actually no need for sequencing element or the flip-flops or the latches or the storage element. They won't be necessary. And since they are not necessary, even the clock itself is not necessary. So for example, if you have this crossroad, the clock would be the traffic light. If you know that everybody is organized and they are spaced equally, and also they have constant speed, we don't need the clock and we don't need the traffic light, and the cars will move smoothly crossing this crossroad without accidents. So it will go like this, and then like this, and then like this without accidents, and there is no need for waiting. There is no need for sequencing. But this is not the case. This only could happen if you have, for example, a fiber optic cable. So in fiber optic cable, the light pulses or the tokens are sent down the cable, and the next pulse sent before the first reaches the end of the cable. So there is no need for hardware to separate the pulses, but dispersion sets minimum time between the pulses. This is called wave pipelining in circuits. So basically, and if you are using light instead of electricity, you don't need clock. You don't need the sequencing. In most circuits, dispersion is high, so you need to delay the fast talking so they don't catch the slow ones. And we do this by applying an organizer, and this organizer is our clock. The sequencing overhead now, we use the flip-flop to delay the fast tokens so they move through exactly one stage each cycle, and the clock is organizing them as we said. inevitably add some delay to the slow token. So you are actually making the fast ones slower. And because this clocking, even the slower ones becomes a little bit slow, and you have this overhead or this delay because of using the clock. But also it makes the circuit slower than just the logic delay. This is called the sequencing overhead. Some people call this clocking overhead, but it applies to asynchronous circuits as well. Inevitable side effect of maintaining the sequence. So to maintain the sequence, you had to pay this price. Now, the sequencing element, the well-known sequencing element that you have studied before maybe, is the latch and the flip-flop. So in the latch, it's actually level sensitive. This is a D latch where you have the D as the input and the Q as the output. And there is the clock that organizes the operation between the D and the Q. It's also called a transparent latch or a D latch. It works like this. When the clock is low, the previous input is stored. If it is high, then you have a transparent latch. In the timing diagram, we call two states, the transparent state and the opaque or the non-transparent state. So for example, if you have the clock low and then high and then low and then high, and you have a certain input like this, goes low and high. Now in the latch, what happens is if you are low, if the clock is low, you are storing the previous value. So whatever is the previous value is stored. If it is 0, you store 0. If it is 1, then you keep storing 1. Now, once you have the clock high, during this whole level, whatever input you have, it will show up in the output after a certain delay. This is why we call it transparent. So when the clock is high, the D or the Q see the D completely, transparently without any interruption. Now, when again you have the clock going low, what you are doing, the Q never see the D at all, doesn't see it. It only stored its previous value. So the previous value here was 0. It continues saving 0. So basically, level-wise, you have storing here, transparent here, storing here, transparent here, and so on. For the flip-flop, it's edge-triggered. It's also known as master-slave flip-flop or D flip-flop or sometimes D register. So you can see that it's similar to this one except of this triangle here. And it shows that this is an edge-triggered flip-flop. What do we mean by edge trigger? On the clock, rising edge. Only at the rising edge, the input is stored and transferred to the output. The timing diagram, usually we have two types, either rising edge trigger or falling edge trigger. So since this example is rising, so at the rising, only at the rising, what happens? It checks the D. So it will be storing everywhere, low, high, falling, low, also this high. You are storing the value. The flip-flop will be transparent only at the rising edge, at this exact moment. So at the exact moment here, it will see what's the value of D. The value of D here is 0, so it will be 0. It will remain 0 until the next rising. Now the next rising, we check the D, we find it to be 1. Now we raise it again to 1, and so on. The flip-flop design, you can read your book that there's some history there that they build it step by step until we reach to the final design. But we've discussed this about in one of the videos before. And we said that in the flip-flop, we have a master latch You can see it here. You have two inverters back to back, and this is the one. And you have the slave. That's another latch. And as you can see, we are having the clock in there. In these two transmission gates here and here. So either you are passing the D or you are storing the D, and you can go back to the video that we've discussed to see the detail of what's going on. Now, it's good to mention here that we are adding actually the inverter here, and we also add it here, and we also add another inverter here. And the reason is to protect the input and also the output. We protect it from the noise, whatever type of noise you have, maybe short sharing, maybe crosstalk, whatever. So these noises are protected in the input because you have an inverter here. Similarly, you have an inverter here and an inverter here. And we chose that, or we chose that this is Q and this is Q bar. Now, if we would like to add the enable, we ignore the clock when the enable is equal to 0. So if the enable is 0, we ignore everything. If not, then the latch of the flip-flop works fine. The mux increases the latch D to Q delay from D to Q. So if you have the mux inside or just here, it's actually increasing this delay. And there is clock gating that could help us as well. So let's look at these in the figures that you see here. So the sample of the latch with enable, you are adding the enable here. In the flip-flop, you are adding the enable here. In the multiplexer design, you have the latch and you have here the enable. And in the enable, either you, in this one, mux, the enable is actually the selector. If the enable is equal to 1, the D will go and it will be here and it works, the latch will work fine. If the enable is equal to 0, what happens is you are actually having a 0 going to the inside the latch. That's the multiplexer design. Now you can do it with a clock gating design where the clock now here 5, it doesn't go here except through the AND. So it's AND gated. So if the enable is 0, there is no clock, it's always 0. If the enable is 1, then you will have a normal clock and the latch work properly. You can have the same scenario with the flip-flop, whether it's through the mux or through the AND that is gating the clock. Now, if we want to add a reset, we can do that. We can force the output low when the reset is asserted. So, but there is two different designs, whether we want a synchronous reset or asynchronous reset. So the synchronous reset waits for the clock. The asynchronous reset right away. So this is the sample. We will add a reset signal here. And for the synchronous resets, you notice that we are now adding this NAND at the beginning of the latch. So this is the latch. This is the normal latch that we studied. And we added this and this NAND circuit. Oh, and the reset here is active low. So if the reset is equal 0, now the value here will be 1 regardless of the value of D. And since the value here is 1, after this inverter, it will be in the Q equal to 0. So the value that you see at the output will be 0. So what you actually did is you reset the latch. However, you will wait for the clock. Even if this result happens to be 1, it won't pass here unless you have the clock. Similarly, for the flip-flop, you have the same idea with the same exact thing, except that you have a flip-flop with 2 latches. Now, for the asynchronous reset, you do the reset in 2 places. At the beginning here, not like the synchronous reset, and also within the flip-flop while you are inverting at the storage or the storing state. So you add the reset here, and we have this NAND that's working with the flow, with the clock. So you reset in both directions. This is for the asynchronous reset, and you can do the same in the also in the flip-flop. And notice here that we are actually doing the reset in the storage or in the storing state, in the master latch and also in the slave latch with the same idea everywhere. It's a NAND with an active low reset signal here and here. And it will show up in the queue as a 0 in every CNAND here, 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 and also. Now, if we want to add a set and a rest, so both of them, comparing this design that we just reached here, to add the set, you will replace this inverter and this inverter with a NAND that do the set signal. And you can have it here. So we replace those inverter with the NAND. You can see it here and here. This NAND doesn't need a clock. This one already covered it. And this one doesn't have a clock, so we need to add a clock over here. And you can see that we have the set signal, and we made it also active low. The difference between the reset and set, the output that shows up in the queue. In the reset, it will be 0. In the set, it will be 1. Now you could do the same. Actually, if you want to change the queue is right there. You take it after this transmission gate, and after that you are inverting to get the queue, or you could have it after the NAND. If you do it that way, then you have to replace the set and reset. So the reset becomes set and the set becomes reset. And you can confirm this by applying some inputs as examples, and you'll see that it is correct. Now for the timing diagram, which is basically the core concept of this talk. The timing diagram, in the timing, we talked about the contamination and the propagation, and we said that the propagation is the long time, the contamination is the short time. And here is some of the samples. This is the propagation delay or the logic propagation delay. This is the logic contamination delay, and it's shown here for a certain circuit, the combinational logic. The A shows up in the Y, or the effect of A shows up in the output, whatever is the functionality of the combinational logic, with sometimes a very short time, which is the contamination time, or it takes sometimes a long time, which is the propagation delay. So you have a short and a long time. We have also a contamination or the propagation clock to queue and the contamination clock to queue. So in a flip-flop, we care about this timing from the clock until you get the queue. And it is having a shorter time, the contamination, and also a longer time. For the latch, we have the propagation D to Q and contamination D to Q. So from D to Q, we care in the latch, usually we care about this time from D to Q. So we have a contamination from D to Q and a propagation from D to Q. We could have in the latch also clock to Q as well, but usually we care about D to Q more than the clock to Q. We have also the setup and hold. The setup or the setup time or the hold time, it could be for the flip-flop or the latch. The setup time is from the critical moment, which is the rising edge. The timing from D up to the rising edge is called the setup. From the rising, when it happens until you get the D is called the hold time, until you really save the value within the flip-flop. Now, in the latch, we have also the setup here after this critical time when you change the level. So you have a setup and you have also the hold time. So these are the definitions of the timings through the different components, combination logic, the flip-flop, and the latch. The sequencing design, there are two trade-offs between the overhead, robustness, and complexity, and constraints on the logic versus the constraints on the clock. And we actually will study three of the famous clocking methodologies. The first one is the edge trigger flip-flop clocking. The second is the two-phase latch clocking. And the last one is the pulse latches clocking. You can see that the flip-flop here, if you look at the design, you have a flip-flop, then a combination logic, another flip-flop. You can see that this flip-flop and this flip-flop work with the same clock. The two-phase transparent latch, actually you have a latch. That's a key difference between that and the edge trigger flip-flops. It's a latch. You have a latch working with a certain clock, phi 1, and then a combination of logic. And then the other latch will work with another flip-flop or another clock, sorry. This latch will work in another clock, which is phi 2. And then another combination logic, and then this repeats. For the pulse latches, you have a latch that works with a certain clock, phi p, and then a combination logic, another latch, and so on. So going back again to find the cycle time for each one of them. The cycle time is from the rising up to the next rising for the flip-flop. For the two-phase clocking, it's actually from the rising of phi 1 until the next rising of phi 1. You can see that they are the same. However, you have the half the cycle here from the rising of phi 1 until the rising of phi 2, if you want to find the half of the cycle time. Also, you have a time here that's very important to us, is the non-overlap time, where both clocks will be storing or low. And in the pulse latches, the cycle time is actually the same from the rising to the next rising. So that's the cycle time for all of them. But here we also care about the pulse width. So if the pulse width is very, very small in the pulse latches, you are approaching the edge triggered flip-flop. And if the pulse width is a kind of large, you are approaching the two-phase transparent latch. So kind of the pulse latches is like it plays in the middle ground between the flip-flop and the two-phase transparent latches. Now, there are times that we need to worry about for each one of these clocking methodology, like the cycle time, the holding time, the borrow time, and the skew or the clock skew time. The three main timing constraints for each type of clocking methodology is the minimum clock cycle, or what we call TC. For example, the cycle time must cover all the timing within the circuits. The maximum holding time, or what we call T hold. So the holding should be less than or equal to the passing time through the previous flip-flop. So from the previous flip-flop until the flip-flop that you want to hold the value in, there is a passing time and there is a holding time. You want to be that holding time to be less than the passing time. Also, we have the maximum borrow time, T borrow. This happens only in the latch systems. So in the flip-flop, there is no room for borrowing. Also, we talked about the clock skew that we need to worry about. We call it T skew. It affects these three timings. The clocks really have uncertainty in arrival time. This will cause a decrease in the maximum propagation delay, or increases in the minimum contamination delay, and also it decreases the time borrow. So it's bad for all these three times that we just mentioned. Not all the clock arrives at the same, or not all the clock arrive at the same time. So some clock might be gated and with control signals, for example. There is also an RC delay associated with the clock. wire. From this discussion of the T skew, they cause two problems. The cycle time gets longer by the skew, so the cycle time that needs to cover all the time of the circuit, now it's also need to cover the skew, which is the delay. And this could happen if in the first flip, the clock signal is late and the second is early. So there is a skew that you need to worry about. The skew is actually the delay on time. So when this clock or when this clock comes late and this is early, so there is a difference between. The other problem is the part can get the wrong answer if you are not careful about the skew, especially if in the first flip-flop, the clock comes early and the second flip-flop, the clock comes late. And if you worry about the holding time must be less than the passing time. Now you need also to worry about the skew. So in that case, the skew will be part of the holding constraint. So if you have a holding against the passing, the hold need to be increased by the skew time. So let's discuss these timings for each clocking methodology one by one. So in each clocking methodology, we will see the cycle time, the holding time, and also the borrowing if there is borrowing. And we will also discuss what will happen if you have a skew for each of these clocking methodology. So the first one is the flip-flops. We will see the cycle time constraint or what we call a maximum delay. And as you can see, if you have two flip-flops, the cycle time must cover all the timings within the circuit, which is from the clock to Q, indicated by TBCQ, and also through the combinational logic indicated by the T propagation delay, and the setup time through this second flip-flop, which is the T setup. So you need to cover that time. So TC must be larger than or equal all of these times. The minimum cycle time is when this is exactly equal to these times. So these are the 3 times that you worry about in the flip-flop. Now, if you have a skew, you make the skew part of the time that you need to worry about, and you can see that we are adding the skew over here. Now for the holding constraint, now I will clarify it more. You need to have, or there is actually a fight going from this flip-flop to this flip-flop. If this flip-flop wants to hold a value in it, it's working on this value and it's trying to store it inside F2. So there is a holding time that happens inside this flip-flop, and at the same time, there is another time that I need to worry about, which is the passing time from the flip-flop until you reach to here. So the typo that you don't want is while you are trying to save a value here, a new value come quickly and mess up your work that you are trying to do in this flip-flop. So we have a holding time within this flip-flop, and we have a passing time through the combinational logic. We should consider the fastest possible time that you can come through this path. This is why we consider the contamination delay. So we need to make sure that the hold time is less than or equal the passing time. And the passing time here is the contamination clock to Q. Notice that we are considering the contamination time. The contamination clock to Q plus the contamination delay through the combinational logic, which is this time, T, C, D. That's the 2 passing times. You need to make sure that the holding time is faster than the passing time, passing time, or the T hold less than or equal the contamination clock to Q plus the contamination delay within the combinational logic. Now, in case you have a skew, then the skew will be part of the holding time. It will be part of the holding time. So the T hold plus the T skew must be less than the passing, less than or equal the passing time. So you will see this in all of the clocking methodology. The T skew is always associated with the T hold when we talk about the holding constraint. It's also good to mention for you that we call this time a minimum delay because if you care about this time, there will be a minimum value for it. A minimum value for it. This is in the opposite of the when we talked about the cycle time. This is called the maximum delay because we care about the propagation delay here, and this propagation delay here has a maximum time for it, since you have larger than or equal. Now, we will jump from the first type. We finished it. Now we will go to the two-phase latches. And by the way, as we mentioned before, there is no borrowing in the flip-flop. So at this point, we checked the cycle time of the flip-flop, we checked the holding time of the flip-flop, and we also checked the time borrowing. We said basically that there is no borrowing in the flip-flop. And we also see the effect of the holding of the skew time at in the holding time and in the cycle time. So let's jump to the next type, which is the two-phase latches. We will see the TC constraint or the maximum delay. Here, since we have two phase latches with phi 1 and phi 2, the cycle time must be the T propagation delay from D to Q. So the propagation from D to Q plus the time through the first combinational logic, TBD1, plus the time from D to Q in the second latch, which is the BDQ2, plus the time through the other combinational logic, which is the TBD2. So it's 2 times for the TBD2Q. So the propagation from D to Q two times, and also the propagation delay through 2 different combinational logics. So the cycle time now need to cover all these 4 times, all the 4 times. Now for this one, the D to Q will be part. It is actually it will be part of the second cycle. Remember, the cycle comes from the first rising of the phi 1 until the second rising of phi 1. This is the definition that we agreed on before. Now for the holding constraints. The holding constraints, again, we have a passing time and a holding time. So the holding time must be less than the contamination clock to Q. Now we worry about the clock to Q because this is the fastest time, not the D to Q. The fastest is from clock to Q, plus the contamination delay through the combinational logic, plus the value of the non-overlapping. So the non-overlapping and the contamination clock to Q and the contamination delay through the combinational logic, all of them part of the passing time. And the holding time must be less than those 3 times. Now, sometimes you consider the CD1 if you are moving from the latch number 1 to latch number 2. And sometimes we consider the TCD2 if you are passing through the opposite from L2 to L1. And know that now the whole time reduced by the non-overlap. And the two-phase latches, actually the whole time is reduced by the non-overlap because you need to cover for it. And there is a paradox. The hold applies twice each cycle for the latches because you have 2 latches versus only once for the flip-flops. But either way, in the flip-flops, inside each flip-flop, you have 2 latches. And you can see the paradox here. Now for the time borrowing, and this is the first time borrowing that we discussed. because in the edge triggers, there is no time variable in borrowing. In the two-phase clocking, you could borrow time to the next half cycle. How? If you have a latch followed by combinational logic, latch followed by combinational logic, another latch, and so on, it keeps going like this. So if this half cycle, this combinational logic needs more time, it could borrow from the next one. So you have borrow time across the half cycle, the boundary. This one, if it doesn't have much time because of the borrowing that happens here, it can push it to the next cycle and so on. So everyone borrowing from the next, every half cycle borrowing from the next half cycle and so on. However, if you have a feedback, if there is a feedback or a loop, the borrow time internally, it could be possible internally, but must complete within the cycle. So you cannot borrow across two different cycles. You borrow within the cycle itself. So if the combinational logic here is long and here is short, then the borrow could happen. So this half cycle borrow from this half cycle and so on, only if you have a feedback. And one way or other, after a while, after a certain number of cycles, there will be a feedback. Now, how much borrowing can we expect? We can calculate this if we know that this is the first half cycle, TC divided by 2, and this is the second half cycle. So we have TC over 2 here as well. So the borrowing time is the amount that I'm trying to borrow here for this combinational logic. This is the borrow time. The borrow time is actually must be less than or equal the TC over 2, which is the half cycle here, but you take out from it the non-overlapping time, because here you are storing the value and you are not passing anything. So you take the non-overlapping time from it, and also the setup time that you have here. And what's left for you is the time that you can give to the first half cycle. This is the borrow time. So as you can see, this is the equation of the borrow. Now, we will leave the adding the skew later after we discuss the pulse latches. So the pulse latches in the cycle time constraint, what happens here, there are two scenarios. One scenario, when the pulse width is larger than the setup time. So here we are saying that the pulse width is kind of large. The second scenario, the pulse width is shorter than the setup time. So the pulse width is almost like the edge. So in A, you are approaching the two-phase latching ways. So if you go to the two-phase latching, we were worrying about 4 times, but here since we have the same pulse, the same clock, 5P, we worry about only 2 times, which is the propagation from D to Q plus the propagation delay through the combinational circuit, because it is like the two-phase latches, since the pulse width is large. So the pulse width, this pulse width is kind of large. If it is very short, so it's very sharp, it's almost a spike, then it's approaching the ideas that we studied in the edge trigger, where the cycle time must cover the propagation clock to Q plus the propagation delay through the circuit plus the setup time, but you take out from it the pulse width, even though this amount of pulse width is very, very small, because it's almost a spike. But to be accurate, this is what you have. So it's propagation clock to Q plus the setup plus the propagation delay through the circuit minus the pulse width. So you have 2 ways. It's based on what's the relation between the pulse width and the setup time. Now, what about the holding constraint of the pulse latches? Again, the whole time increased by the pulse width. Is that like the what we seen in the two-phase latches, where we have the non-overlapping? Now, equivalent to the non-overlapping is the pulse width. So the whole time plus the pulse width is less than or equal the clock to Q plus the contamination clock to Q plus the contamination clock through the circuit. This is the passing time now. So in the passing time, we have the clock to Q and also to DC, to the TCD. And here we have the pulse width, and we will consider it part of the holding time. That's the difference between the pulse width and the non-overlapping. The non-overlapping is part of the passing time and the two-phase clocking, but the pulse width here is part of the holding time, which will show up here. Now about the borrowing. The borrowing in the pulse latches. There could be some borrowing in the pulse latches, but it's very, very small. It's almost negligible. And this is happening only if the pulse width is bigger than the setup time, meaning that the pulse width latches is approaching the two-phase clocking. So now the pulse latches could be capable of a very tiny amount of the borrowing. You can calculate it this way. The T borrow, which is this time, is actually the pulse width, and you take out from it the setup time. So the T borrow is less than or equal to the pulse width minus the setup time. The maximum time that you could borrow equal exactly the pulse width and taking out from it the setup time. So it's pulse width minus the T setup. Now, after we discuss the cycle time and the holding time and the time borrowing for both the two-phase latches and the pulse latches, we will see what will happen with them when you add the skew in all of them. So for all the latches, whether they are two-phase latches or the pulse latches, what will happen with this skew? In the cycle time constraint for the two-phase latches, there is no effect related to the skew because you have two different clocks. They are absolutely two different clocks. So you're not worried about one of them having or being late and the other is there. They are actually two different clocks. But for the holding constraint, you add the skew with the holding time. Similarly, for the pulse latches, in the holding constraint, you add it in with the skew is always with the hold. You can check also the edge trigger. You will find always in the holding constraint, the skew is part of the holding. You add it with the hold. Now, as we said, in the cycle time, there is nothing, the skew doesn't affect the two-phase latches. In the pulse latches, it has an effect. It's a small effect, but it's there. And again, this is if you are or the pulse latch is behaving like the two-phase latch, which is this one, there is no skew in the equation. But if it is approaching the behavior of the edge trigger, then you will have a skew that you need to cover as well. So you cover the timing within the circuit and also the skew. Now, what's the effect of the skew in the time borrowed? You know that the time borrowed is half the cycle in the two-phase latches minus sometimes the non-overlap and the setup, and also you take out the skew. Similarly here is the pulse width, and you take out the setup from it, you also take out the skew. So in the borrow, it's close to or it's associated with the setup. The skew becomes associated with the setup. Also here, the skew is associated with the setup. So in summary, we've seen two or three clocking methodologies. The flip-flops are very easy to use, supported by all the tools. The two-phase transparent latch, there is lots of skew tolerance. The skew doesn't affect much. And also there is time borrowing that you can get advantage of. In the pulse latches, it's fast. There is some skew toll and also borrow, but there is a hold time risk. And the risk is also there for both of them, but the risk is here. It's a little bit higher. We summarized all these equations that we discussed in this table. You can, some of the hints here that you can see, like there is no time borrow here in the edge trigger flip-flop, while you have a borrow in the two-phase and also in the pulse latches. If you talk about the skew is always added as part of the time that the cycle time needs to cover. So it's always here. But in the two-phase latches, there is no effect of the skew at all. In the pulse latches, it's only here that you need to cover it. For the holding constraint, the skew is always associated with hold, as you can see in every equation. For the time borrow, there is nothing here in the flip-flop. Here and here, the skew is always associated with the setup as we mentioned. This is what we want to talk about on the sequential circuit design. There is many aspects, other aspects that you can read the book if you are interested. Next time, we will talk about another subject. We will talk about the power consumption. Also, after that, we will talk about the main memory and how to deal with the main memory. Also, there is another subject that is not related to memory and the power consumption directly, which is the testing, how you make the circuit testable. So we will talk about these three times or these three subjects later, specifically the power consumption, the main memory, and also the testing.